Friends, today I am now going to start a very important series on tensors, and it is included in the series of matrix. I am including this series in the series of matrix. So firstly, today I am going to introduce with you tensors, and in my next videos I will elaborate about tensors more. So let's start. So first of all, you should clear about what is tensor. Okay, what is tensor? We all know vector, we all know scalar, but what we know about vector, that it has direction and it has magnitude. And what we know about scalar, it has only magnitude. But you should ask, then what is tensor? So let's discuss. Before going to the definition of tensor, I will call some physical quantity as a non-vector quantity. After that, we will discuss the definition. So, I'm going to write some physical relation, that is F equals m into a vector, J equals sigma into E vector, P equals F psi into E vector, M equals chi into H vector. So I am writing such physical relation, etc., etc. I have written some such physical example. So here F equals ma, we all know what is this. We all know this is the one of the Newton's equation of motion. And here m, you will call what is m. The student who is very much at his basics studies of physics, he will call it is scalar or etc. But I will not now call it scalar. I will now define it as non-vector quantity, such as sigma. J equals sigma. In this physical relation, what is sigma? Sigma is conductivity. Such as P equals alpha is this polarizability relation. P equals F psi or M equals chi into H. I am noting down these quantities are not a scalar. This is vector because it has arrow above head. It has magnitude and direction. But what is this quantity m? What is this quantity sigma? So this is non-vector quantities. So in these cases, we have taken that non-vector quantities to be scalar. But when we are now, I am making you understand what is the difference between these non-vector quantities or otherwise tensor quantities and the so-called scalar quantities. First of all, we have to know that when we are writing F equals m into a vector, when we are writing F equals m into a vector, then m is scalar at isotropic medium. Yes, at isotropic medium, when we are considering Newton's equation of motion, F equals ma in an isotropic medium, then we will call it scalar. But when we are writing F equals m into a vector, when we will write m in anisotropic medium, in anisotropic medium, we will call it not as scalar, we will call it tensor. That means this physical quantity, we will call it tensor in anisotropic medium. That means if the medium is anisotropic, I am writing a relation. First of all, I am writing a relation. That means if in such case, if the medium is anisotropic, I am writing a relation such as a vector equals alpha into b vector. Such as here I have written F equals m into a vector. So what we can write, m equals a vector by a vector. Similarly, what we can write here, alpha equals a vector by b vector. So in case of this tensor relation in an anisotropic medium, A is written as cos vector. Let me write in clear space. In case of anisotropic medium, when we will write such relation A equals alpha into b vector, there A is written as cos vector and cos vector here I am writing, and B is written as effect vector. B is written as effect vector. So if the medium is anisotropic, then effect vector produced will not, if the medium is anisotropic, that is non-isotropic, anisotropic, then the effect vector, this effect vector produced will not be same direction as cos vector. I am discussing this by F equals ma. So I am now entering into the definition of the tensor, or how we will call such a physical quantity, some physical quantity, as a tensor. Here I am writing this relation F equals ma and m equals, so A equals alpha into b vector. Here we have written A is cos vector and B is effect vector. So in case of isotropic medium, what we know, when if F vector has same direction, then A vector has same direction, such as we have applied a force on a body at x direction, then acceleration will be also on x direction. This is for isotropic medium. But in case of anisotropic medium, A vector equals alpha into b vector, where A is the cos vector. Then this is the effect vector and it is the cos vector. Then effect vector produced will not be a same direction as cos vector. That means in anisotropic medium, effect vector is not as same direction as cos vector. Such as if F equals ma I have written in anisotropic medium, then A has not same direction as F vector. Then we will introduce the definition of tensor. So now if we are going to write tensor mathematically, how we will enter the mathematical definition of tensor. So then what we conclude from the physical definition of tensor, if in anisotropic medium that A vector equals alpha into b vector, this relation, this cos vector, this effect vector, this vector produced due to this effect vector is not along the same direction as A vector. B has not same direction as A vector. Then we will introduce the idea of tensor. So let's introduce the idea of tensor mathematically. Otherwise, how can we prove? We have to prove everything in mathematics. So for that, we have to write linear transformation. So what is linear transformation? So for that, we have to know the vector space. So in case of vector, what we have seen, vector has 3 dimensions. And in case of tensor, what we will see, in case of tensor, we will see greater than 3 dimension. That means we can write a tensor has n dimension. N tends to infinity. That means greater than vector dimension. Now I'm going to discuss about the linear transformation. If we call a vector space Vn, that is n dimensional vector space or n dimensional space, you can call it only space to avoid the confusion. So if Vn is the n dimensional space where x1, x2 dot xi, xn be the coordinates of the point with respect to one frame of reference, be the coordinates of the point with respect to one frame of reference, and if x1 bar, x2 bar, xi bar dot xn bar for the same point with respect to another frame of reference, then I am representing them as a set quantity. So it is coordinates xi set and it is coordinate x bar, let me write clearly, and it is coordinate x bar p as represent the same point with respect to two coordinates. So these sets represent same point with respect to two coordinates. The coordinates in one system will be related to coordinates in another system, such as, so I am giving the relation between them. X bar p equals, we'll write x bar p x1 x2 dot xn. Similarly, we can write xi will be related to xp as xi equals xi function of, or x1 bar, x2 bar, xq bar dot xn bar. So we can write as a linear transformation. We can write the coordinate as xp bar. You can write xp bar. You can write alpha p1 x1 plus alpha p2 x2 plus dot alpha pn xn. So we have same points xi and xp bar. We have same points xi and xp, they are same point but with respect to two coordinate system, and the coordinate system has relation by linear transformation. This xp bar equals alpha px1 plus alpha p1 x1 plus alpha p2 x2 dot alpha pn xn for n dimensional Vn space. So there this transformation is said to be linear. Then we can generalize that linear relation as, so we can generalize the linear relation as xp bar. Let me write clearly here. xp bar equals summation over I equals 1 to n alpha pi xi. So this transformation is linear transformation. So it is a linear transformation of what? Try to understand this now. So I have written a linear relation between two coordinates of same point. Writing here clearly. Same point means a point, this is a point, such as this is a point where it is the same point, but I have written one coordinate, this is as xi, and in another coordinate I have written as xp bar. So this two coordinate system has linear relation given by xp bar equals alpha pi xi. So this alpha is said to be transformation coefficient, or you can say transformation matrix. So this alpha can be written as alpha pi, and in matrix form how we can write that? This transformation matrix we can write as alpha 1 1, alpha 1 2, alpha 1n, alpha 2 1, alpha 2 2, alpha 2n, alpha n1. Let me write clearly. Alpha n1, alpha n2, alpha nn. So this is the transformation matrix. This is the transformation matrix alpha, by which we are relating two coordinates on same point. So this transformation matrix, and if we, it is actually that we are actually entering the definition of tensor. So what we are getting? So if we take the determinant, of the matrix, then it will be called as what? Transformation determinant. And so let me write. So transformation determinant will be written as alpha 1 1, alpha 1 2, alpha 1n, alpha 2 1, alpha 2 2, alpha 2n, alpha n1, alpha n2, alpha nn. So this is the transformation determinant, and from this transformation relation what we are getting? We are getting that alpha pi equals del x bar p by del x I, according to then I and p according to n dimensional space 1, 2, dn. Then we can write xp bar equals summation over I equals 1 to n del x bar p del x I del x I. This is the relation. Number of partial derivative in transformation rule is defined as rank. So what we get today? So we get today relation between, later we will call this as contravariant vector or contravariant tensor, and covariant vector covariant tensors, this relation. So we get today the definition, physical definition of tensor as, if cos vector it is and it is the effect vector, if effect vector B is caused by A, the ratio of cos vector and effect vector, A equals alpha into B, then the ratio of cos vector by effect vector in anisotropic medium is written as tensor. And after that we have described the transformation relation and some transformation determinant. So for today's introduction, it is just the today's introduction part of tensor. So thank you.